Hey, I'm Michael, and today I'll show you how to make an eye tracker with Open. What we'll be making is a program that automatically detects where you're looking on the screen and then moves your mouse there, essentially allowing you to control your mouse with your eye movements. The algorithm consists of 4 steps. The first step is locating your face. The second step is locating where your eyes are on your face. The third step is locating your pupils within your eyes. And the fourth step is converting those pupil locations to screen coordinates. Start by importing OpenCV and then creating a video capture. This reads the data from the webcam. Then we'll have a loop that continuously captures data from the webcam and then displays it on the screen in a window called frame. Then we want to be able to exit our program if we want to, so we'll add a line that checks to see if the Q key was pressed and then automatically exit the program if that happens. This wait key command is required to make the image actually show up. Otherwise, cv2.imshow will do nothing. If I run this program, then we'll be able to see the webcam footage and therefore we'll be able to see ourselves. We can start with face detection and landmark detection. Landmarks are just key points on the face like the crease of the eye. So first we import DLib and then we load the default face detection model. This will return a function that we can use to find the bounding boxes of faces, and then we can draw them on the screen with OpenCV. So if we run the code as it is right now, a rectangle will appear on my face. If we now want to detect the landmarks of our face, like the crease of our eye, which are useful for the eye tracking, we import the DLib shape detector model, and then we find the landmarks on the face within the bounding box. And then we draw the landmarks on the screen with OpenCV's graphics, whatever. And then I run this program, and now all the facial landmarks are displayed. So we have the facial landmark detection working and the face detection working. Now we want to find bounding boxes around each eye. So the landmarks are actually in a very specific order, so that if we select landmarks 36 through 42, it'll give us the landmarks around the left eye. And if we select landmarks 42 through 48, it'll give us the landmarks for the right eye. And so then we can just find the bounding box around these landmarks by writing a function for that. So we just find the minimum and maximum x and y coordinates. And now these left b box and right b box variables will correspond to rectangles around the eyes. So then we can draw these with cv2.rectangle, the graphics function. When I run the program, rectangles will show up around my eyes. Now that we have the bounding boxes of the eyes, we can crop out the eyes and locate the iris. So to do this, we'll first crop out the eyes according to the bounding boxes that we found earlier, and we'll just write a helper function called crop to do this. And this helper function will just select the part of the image corresponding to the bounding box, this being the min and max y value, and this being the min and max x value. After that, we write a helper function to filter for the iris based on the cropped frame. So because this frame is in color, we first convert it to grayscale using cv2.cvtcolor, which means convert color. And then we blur the frame. These parameters here specify the radius of the blurring. Then we adjust the brightness such that there's an equal amount of light parts of the image compared to dark parts of the image. This is called equalizing the histogram, and we do this with cv2.equalizeHist. Then we find the dark parts of the frame. This is through a binary threshold. So we do cv2.threshold, and this is the image we want to threshold. Any pixels that are brighter than 50, coming from a range of 0 to 255, will get converted to 255. This function returns 2 values, a ret and the actual result. We only want to select the actual result, so we'll just index for 1 here. The reason we subtract this from 255 is that this will mean all the bright parts of the eye will be converted to 255, and we want to select for all the dark parts of the eyes. After this, we return the iris image, and then we can display the resulting iris frames with OpenCV.imshow. So running this, the iris of the eye gets highlighted in white. We'll just clean up some of this code so that we don't have all of our annotations cluttering the screen. Now we're going to write a function that finds the center of the iris. We're going to call this find iris location. So given an image of the iris, first we find all of the connected blobs of bright pixels with CV2's find contours method. Then we will sort the contours in ascending order by area, and then we'll try to find the center of the largest contour. And to do this, we'll use something called image moments. And what image moments do is they find the weighted average of the x value and the weighted average of the y value. So moments M1, 0 finds the sum of all the x values weighted by brightness, and moments M01 finds the sum of the y values weighted by brightness, and then moments M00 just finds the sum of all the brightnesses without regard to x or y. We assume that if there was no contour found, an index error will be raised, and if there are no bright pixels at all, we would have divided by 0 here, so then we'll get a 0 division error. So therefore, if we get either of these two errors, there will be no iris in the picture, so we just return none. Otherwise, we'll turn the location of the iris. Finally, we will draw these locations on the screen. Little indicators will show up in the center of my irises. So now that we know where the center of the iris is, we can find out which direction you're looking, find out where on the screen you're looking, and finally, move the mouse to where you are looking on the screen. We're going to do this by taking the center of the iris and comparing it to the center of the eye. So therefore, if you're looking to the right, then your iris will be at a slight offset compared to the center of the eye. So we'll store these offsets in variables, and then we'll calculate the offset by simply comparing to the center of the eye with subtraction. Then to find the center of the eye, we will use the landmarks generated by DLib. So the opposite sides of the eye, sort of the creases of the eye, are landmarks 36 and 39 for the left eye, and 42 and 45 for the right eye. We make sure that we have both offsets, and then we calculate the average offset. So this is just the offset in the right eye and the offset in the left eye, taking the average of those two. Then we're going to use some calibration. We'll use the offset of your left and right eye when you're looking at the top left part of the screen and the bottom right part of the screen as reference points to calculate the rest of the locations. So if we need to calibrate, then we'll tell the user to look at a specific part of the screen, and then after a short time delay, we'll record the offset of the iris relative to the center of the eye. So in order to have a time delay, we need to store the last time we told the user where to look on the screen. So we'll do that by creating a variable called last time I told the user to look somewhere. It's a long variable name, but it's descriptive. So if this value is none, then that means we haven't told the user to look anywhere yet. So if you haven't told the user to look anywhere yet, then we'll look and see which calibration points do we have. If we do not have a reference point for the top left part of the screen, we'll tell the user to look at the top left corner. Otherwise, we'll tell them to look at the bottom right corner. Then we'll import time so that we can store the last time that we told the user to look somewhere with time.time. Then, if we have told the user to look somewhere, then we check to see if the current time is at least 5 seconds after we told the user to look somewhere before. If it is, then we see if we needed the top left reference point or if we needed the bottom right reference point. If we needed the top left reference point, then we'll store the current offset in the top left reference point. If we needed the bottom right reference point, then we'll store the offset in the bottom right reference point. Now, we remember that we didn't tell the user to look anywhere relevant anymore, so that we set this value to none. So if we don't need calibration, then we can use these reference points to automatically detect where on the screen the user is looking. So we'll destructure these two variables, and then we'll use the library Pyautogui to automatically move the mouse to a specific location. So we'll import Pyautogui, and then we'll set the fail-safe option to false. And what this does is it means the program doesn't automatically exit when the mouse moves to the top left side of the screen, because that might happen if we avert our eyes to the top left side of the screen and we don't want the program to just exit because of that. If we do want to use the mouse without being kind of interfered with by the eye tracking, then we can just cover the camera and then move the mouse freely. So then we interpolate between the two reference points and scale up to the dimensions of the screen, and then move to that location with Pyautogui.move2. Then, when I run this program, it'll tell me to look at the top left corner, And it'll tell me to look at the bottom right corner. And then I'll cover the camera so that I can open the window. Wherever I look on the screen, the mouse will automatically move there. So right now I'm looking at the right side of the screen, and the mouse is towards the right side. If I look at the left side of the screen, then the mouse will move towards the left side. And if I look towards the bottom of the screen, the mouse will move towards the bottom of the screen. If I look towards the top of the screen, the mouse looks towards the top of the screen. So this allows for a very general mouse movement control with pure eye movements. And I think that's pretty exciting, because even though this amount of control is not very precise, it does allow for some control without using any hand movements, any voice commands, or anything except for eye movements. So it opens doors to a lot of interesting things. That's the whole tutorial. Please leave any questions or comments in the comment section below. Thank you.